There is a rule written into the fabric of the cosmos. A rule so fundamental that every star in the night sky obeys it. A limit. Not a law made by humans, but one enforced by gravity itself. Stars can only grow so big. Beyond a certain size, pressure loses control. Gravity wins. The star collapses or explodes. For billions of years, astronomers believed this limit was absolute. No exceptions, because stars are not balloons. They are battles. Inside every star, two unimaginable forces fight endlessly. Gravity tries to crush it inward. Nuclear fusion fights back, pushing outward with energy created at the core. As long as these two forces remain balanced, the star survives. But when the balance breaks, the universe does not hesitate. Small stars shrink into white dwarfs. Massive stars detonate as supernovae. The most extreme collapse into black holes. Nature does not allow indecision. That is why astronomers were confident. There is a maximum size a star can reach before it destroys itself. Yet somewhere deep in our galaxy, far beyond naked human sight, exists a star so enormous that it shatters that belief completely. A star so large that if placed where our sun sits now, its surface would stretch beyond the orbit of Saturn, possibly even farther. A star so swollen that light itself struggles to escape its outer layers. A star so unstable that, according to physics, it should not exist at all. And yet, it does. Its name is Stephenson 2-18. And when astronomers realized what they were looking at, they checked their data again, and again, and again. Because surely, something this large had to be a mistake. To understand why this star terrified scientists, we must first understand something humbling: how small our sun really is. The sun feels enormous to us. It contains more than 99.8% of all mass in the solar system. You could fit 1.3 million Earths inside it. Light takes over 8 minutes to reach us. Its gravity binds planets across billions of kilometers. Yet in the universe of stars, the sun is nothing special. It is a yellow dwarf. Average, stable, modest, a quiet flame compared to the giants that roam the galaxy. Even so, our sun already holds us hostage. If it expanded just a little, Earth would be destroyed. When it eventually becomes a red giant in 5 billion years, it will likely consume Mercury and Venus, and possibly Earth. That seems catastrophic, until you compare it to what exists elsewhere. Some stars are tens of times larger than the sun, others are hundreds. But Stephenson 2-18 exists in a category that almost feels obscene. Its radius is estimated to be over 2,100 times larger than the sun. To put that into perspective, if the sun were the size of a basketball, Stephenson 2-18 would be taller than Mount Everest. If it replaced our sun, its surface would extend past Jupiter, past Saturn, possibly brushing Uranus. Our entire solar system would be buried inside a single star. And this isn't science fiction. This is an object astronomers actually observe, which is why its existence is so disturbing. Because stars this large should tear themselves apart. Gravity should crush the core. Radiation pressure should blow the outer layers away. The star should collapse, or explode, or become something else. But it hasn't. It lingers, bloated, pulsing, barely holding together, like a cosmic anomaly frozen between life and death. When scientists first detected Stephenson 2-18, they weren't even searching for giant stars. They were mapping red supergiants in a cluster known as Stephenson 2, discovered in 1990. At first, the star appeared unremarkable, just another red point in the infrared spectrum. But when researchers measured its brightness, something felt wrong. It was too luminous, too diffuse. Its energy output didn't match its apparent temperature, which meant only one thing. The star wasn't small and hot, it was enormous and cool, and that combination is rare, because as stars expand, they usually lose mass rapidly. Their outer layers drift away into space, they cannot stay inflated for long. Yet this star had expanded far beyond expected limits, and stayed there. That's when doubts began. Was the distance wrong? Was the brightness miscalculated? Were astronomers confusing multiple stars for one? They rechecked everything, using infrared telescopes, using spectroscopy, using stellar evolution models. Each time, the numbers returned the same message. This star is impossibly large, and it should not exist in its current form. Which brings us to the first unsettling realization. Stars are not solid. They have no surface you could stand on. Their edge is a fading boundary of plasma, meaning a star this large is not dense, it is thin, ghostly, more like a glowing atmosphere stretching across billions of kilometers. Stephenson 2-18 is so expanded that parts of it are barely held by gravity at all. Atoms drift, matter escapes. The star is slowly bleeding itself into space, yet it remains intact, for now, and that for now matters, because stars this massive do not die gently. When they go, they rewrite their surroundings. A supernova from a star like this would release more energy than the sun will emit in its entire lifetime. If it collapses into a black hole, space-time itself would shudder. If it destabilizes asymmetrically, it could emit gamma-ray bursts, beams so powerful they can sterilize planets across galaxies. This is not just a big star, it is a loaded weapon written into the galaxy. And it exists right now, somewhere out there, quiet, glowing, waiting. Every star in the universe begins the same way. Not with fire, not with light, but with silence. Cold clouds of gas drift through space for millions of years. Vast, invisible oceans made mostly of hydrogen. These clouds are calm. Nothing dramatic happens, until gravity finds a weakness, a slight ripple, a nearby supernova shockwave, a passing star. Something nudges the cloud, and once gravity begins pulling inward, it never truly stops. Gas collapses, density increases, temperature rises. At the center, pressure becomes unbearable. Atoms crash together at unimaginable speeds. And then, fusion ignites. A star is born. At first, stars are simple. The more mass they gather, the stronger gravity becomes. The stronger gravity becomes, the hotter the core burns. This is the key rule of stellar evolution: mass determines destiny. Small stars burn slowly and live trillions of years. Medium stars, like our sun, shine calmly for billions. Massive stars burn violently and die young. They are born screaming and die screaming. But here is the crucial part. As stars gain mass, they also approach a limit. Too much mass creates too much gravity. The core compresses, fusion accelerates, radiation pressure explodes outward. The star becomes unstable. At that point, one of three things must happen. The star sheds mass, the star collapses, or the star explodes. There is no fourth option. This is not theory, this is observed. Across the galaxy, massive stars constantly lose their outer layers. Powerful stellar winds rip material away at millions of tons per second. Nature enforces balance, except not always. Red supergiants form when massive stars exhaust hydrogen in their cores. Fusion shifts outward. The core contracts. The outer layers swell dramatically. The star expands. Cooler surface. Red glow. These stars are enormous. Hundreds, sometimes over 1,000 times the sun's size. But they are temporary. They are dying. Their expansion is unstable. They cannot remain bloated for long, which makes Stephenson 2-18 deeply unnatural, because it is not just large, it is too large for the mass it has. Its gravity should not be strong enough to hold its outer layers together, and yet they remain, like fog refusing to disperse. This contradiction forced astronomers to confront an uncomfortable possibility. Maybe our understanding of stellar structure is incomplete, or worse, maybe this star is not behaving like a star at all. Some researchers began to wonder whether Stephenson 2-18 was misclassified. Perhaps it wasn't a single object. Maybe it was a cluster. Maybe dust distorted the measurements. But repeated observations eliminated those explanations. The light spectrum showed a single stellar source. The absorption lines matched one object. The data refused to cooperate with skepticism, which leads to something deeply unsettling. Stars are not passive objects. They are dynamic systems governed by equations. And those equations predict collapse at this scale. If a star ignores those equations, then either the equations are wrong, or something unknown is happening inside. This is where fear begins to creep in. Because the interior of a star is hidden, we cannot see inside. We infer, we calculate, we model, but we do not observe. Everything we believe about stellar cores comes from theory, and theories work until they don't. Stephenson 2-18 sits right at the edge of theoretical failure. Its luminosity, temperature, and size do not align cleanly. It behaves like a star that should already be dead, yet it remains alive. Barely, like a heartbeat continuing long after it should have stopped. Some astronomers suspect the star may be in a brief transitional phase, a moment so short that catching it would be astronomically unlikely. Yet here it is, observed, persisting, which implies one of two terrifying possibilities. Either we are witnessing a cosmic coincidence of impossible timing, or this phase lasts longer than we believe. meaning stellar evolution behaves differently at extreme scales. Neither option is comforting, because if stars can exist longer in unstable forms, then supernova timing becomes unpredictable, and unpredictability in astrophysics is dangerous. Massive stars do not just die quietly. When they collapse, they flood their surroundings with radiation. If one were close enough, and thankfully this one is not, it could sterilize entire regions of space. Gamma-ray bursts from collapsing hypergiants can be lethal across thousands of light-years. Stephenson 2-18 is too distant to threaten Earth, but it is not unique. If one exists, others may too. Hidden, undetected, waiting. And here lies the deeper problem. Astronomers estimate there are hundreds of billions of stars in our galaxy alone. We have carefully studied only a tiny fraction. Most exist unseen behind dust. Infrared surveys reveal giants we never knew were there. Which means Stephenson 2-18 may not be an exception. It may be a warning, a sign that the upper limits of star size are not firm boundaries, but soft suggestions. And if that is true, then the universe may be capable of producing objects far beyond our expectations. Objects so large, so unstable, so energetic, that our models simply cannot predict their behavior. This brings us to the most frightening truth of all. The universe does not need permission to break our theories. It does not care what we believe is possible. It only obeys deeper rules, rules we may not yet understand. And stars like Stephenson 2-18 sit at the edge of those unknown rules. They are not just celestial objects, they are stress tests. Reality pushing itself to see what it can tolerate. If you could somehow fall into Stephenson 2-18, you would never touch a surface. There is no ground, no crust, no solid boundary, only layers upon layers of glowing plasma, thinning as you drift outward, thickening as you sink inward. At first, it would feel gentle. The outer atmosphere of this star is so diffuse that it is closer to a vacuum than air. You could pass through millions of kilometers before feeling serious resistance. But that calm is an illusion. Because deeper inside, conditions become violent beyond comprehension. Pressure increases relentlessly. Temperatures rise into the tens of millions of degrees. Atoms are torn apart. Electrons ripped from nuclei. Matter becomes something else entirely. A sea of charged particles fighting gravity every second. At the heart of most stars lies a core burning hydrogen into helium, but Stephenson 2-18 passed that stage long ago. Its hydrogen fuel is gone. That's what makes its size so terrifying. When hydrogen fusion ends, stars do not stabilize, they destabilize. The core contracts, gravity tightens, temperatures soar, new fusion reactions ignite. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes neon. Neon becomes silicon. Each stage burns faster than the last. Hydrogen lasts millions of years. Helium lasts hundreds of thousands. Later stages burn for years, then days, then hours, and eventually, seconds. This is the countdown to death. Every massive star follows this sequence. And when iron forms in the core, fusion stops. Iron does not release energy when fused, it consumes it. At that moment, the star loses the battle. Gravity wins instantly. The core collapses at a quarter the speed of light. In less than a second, a structure larger than Earth is crushed into something the size of a city. The rebound triggers a supernova. But here's the unsettling part. Stephenson 2-18 is so massive that its evolution may not follow this clean path. Its core may already be unstable, already collapsing, already forming dense regions of matter, silently. We wouldn't know, because the light we see left the star thousands of years ago. We are watching its past. The star we observe today may already be gone, exploded, collapsed, or transformed into something else entirely. Astronomy is haunted by this delay. Every star you see may already be dead. And with giants like this, the delay is terrifying, because their deaths are not subtle. They do not fade. They detonate. Or worse, they fail to explode at all. Some stars collapse directly into black holes. No supernova, no warning, just silence. A star vanishes. Stephenson 2-18 may be massive enough to do exactly that. Its core could collapse inward and never rebound. The outer layers would fall in. Light would disappear. A black hole would form quietly, and the universe would barely notice, except for a brief gravitational shudder. That possibility frightens astrophysicists, because black holes formed this way are unpredictable. They do not announce themselves. They simply appear. But there is another possibility, far more violent: hypernova. A supernova so powerful it outshines entire galaxies. Only the most massive stars can trigger them. and Stephenson 2-18 sits dangerously close to that category. A hypernova releases as much energy in seconds as the sun will produce in its entire lifetime. It floods space with radiation, it forges heavy elements, it tears apart its own structure completely. In some cases, it produces gamma-ray bursts, focus beams of energy traveling near light speed. If aimed at a planet, they strip atmospheres, erase ozone, trigger mass extinctions. Thankfully, Stephenson 2-18 is far too distant to threaten Earth. But again, distance does not remove significance, because stars like this shape galaxies. They seed space with the elements needed for planets and life. Every atom of gold, uranium, and many heavy elements comes from deaths like these, which means monsters like Stephenson 2-18 are not mistakes, they are creators. But creators with terrible cost. The deeper scientists modeled this star, the more inconsistencies appeared. Its mass loss rate is enormous. Its outer layers are unstable. Shockwaves ripple through its atmosphere. It pulses, expands, contracts, as if struggling to remain intact. Astronomers describe it as barely holding together. Others describe it more bluntly, it is a star in the act of failing. And that phrasing matters, because failure in astrophysics does not mean malfunction, it means transition. Something about to become something else. The problem is, we don't know what. Stars this large occupy a region of stellar evolution where data is scarce. There are very few known examples, and each behaves differently. Some collapse, some explode, some shed mass violently and shrink, some disappear behind dust. There is no universal outcome, which makes prediction nearly impossible. This uncertainty unnerves scientists more than danger, because predictability is safety, and Stephenson 2-18 refuses to be predictable. Its internal structure may be fragmented, its core may not be spherical, rotation may be distorting fusion zones, magnetic fields may be warping energy flow. Small asymmetries inside a star this large can amplify catastrophically. A slight imbalance becomes a runaway collapse. A tiny fluctuation becomes annihilation. The star is so large that its own size works against it. Communication inside the star is slow. Energy takes time to travel outward. The core may collapse long before the outer layers know anything is wrong. By the time information arrives, it's already too late. This delay could produce one of the most violent stellar deaths imaginable, or a quiet vanishing. No one knows, and that not knowing is the point. Stephenson 2-18 exposes a weakness in our cosmic understanding. We are good at predicting average stars. We struggle at extremes. The universe, it seems, saves its most dangerous behavior for the edges. In the universe, size is power, not political power, not conscious power, physical power. Massive stars do not merely shine, they rewrite their surroundings. Stephenson 2-18 is not just a giant, it is a gravitational event waiting to happen. Even while alive, stars this large are changing space around them. Their stellar winds are so strong that they eject material at millions of tons per second, not gently, violently. Entire shells of gas are blown outward, forming expanding bubbles tens of light years wide. These bubbles collide with surrounding gas clouds. They compress them, triggering new star formation. In this way, massive stars are both destroyers and creators. They kill regions of space with radiation and give birth to new stars in their wake. This cycle has been happening since the universe was young, and without it, planets like Earth would never exist, because the early universe contained almost nothing but hydrogen and helium. No oxygen, no carbon, no iron, no calcium in your bones. Those elements are forged inside massive stars, and only released when they die. Everything solid you've ever touched was born in explosions like the one Stephenson 2-18 will one day unleash, which is humbling, but also terrifying. Because life exists only because the universe is violent. Peaceful universes are empty universes, and giants like this remind us of that uncomfortable truth. Astronomers now believe the Milky Way's structure has been shaped largely by generations of massive stars. Their death sculpts spiral arms, their radiation clears paths through dust, their gravity influences stellar motion. In many ways, galaxies are built by monsters. But here's where the story turns darker, because these same stars may also be responsible for extinction. On Earth, we think of extinction as geological or biological, asteroids, volcanoes, climate shifts. But cosmic events leave fingerprints too. Some researchers suspect that gamma-ray bursts from distant massive star collapses may have affected Earth in the deep past, not directly destroying life, but weakening ecosystems, stripping ozone, increasing mutation rates. Subtle, invisible damage. enough to tip fragile systems over the edge. We cannot prove this conclusively, but we know gamma-ray bursts occur. We know they are devastating, and we know Earth has survived billions of years in a galaxy full of dying giants, which means survival is not guaranteed. It's fortunate. Stephenson 2-18 is not aimed at us, but its existence reminds astronomers of how vulnerable life really is. We live in a calm corner of a violent cosmos, a quiet suburb surrounded by supernovae. This realization has changed how scientists think about habitable zones. It's not enough for a planet to be the right distance from its star. It must also live in the right neighborhood. Too close to massive stars, and life never stabilizes. Too many giants nearby, and radiation resets evolution repeatedly, which may explain why intelligent life seems rare. The universe is not hostile, but it is careless, and giants like Stephenson 2-18 embody that carelessness. They do not intend harm, they simply exist. But there is another layer to this story, one even more unsettling, because these massive stars were far more common in the early universe. The first generations of stars, known as population 3 stars, were titanic beyond imagination, hundreds of times more massive than our sun, short-lived, violent, exploding within millions of years. They lit up the darkness after the Big Bang. They forged the first heavy elements. They transformed the universe from simplicity into complexity. And then they vanished. None survive today. But Stephenson 2-18 may be a distant echo of that ancient era, a reminder of how extreme the universe once was. Some astronomers believe it may represent the upper boundary of what stars can still become, a final relic of cosmic excess. If so, then we are witnessing a dying tradition, the last breaths of an era where nature experimented with size, where gravity pushed limits, where matter gathered recklessly. The modern universe is calmer, more restrained. Entropy has smoothed the extremes. But occasionally, something slips through, a giant forms anyway, and refuses to obey expectations, which brings us to the quiet truth beneath all of this. The universe is not finished evolving. Its rules are not frozen. They adapt, shift, relax. Stars like Stephenson 2-18 appear when conditions align just right. They are not mistakes. They are reminders that the cosmos still explores its own possibilities, and exploration is never safe. Stephenson 2-18 does not threaten Earth. It will never reach us. Its death will not tear our skies open. Its light will fade quietly into history, and yet, its existence changes something fundamental, because it forces humanity to confront a truth we rarely like to face. The universe does not scale to us. We scale to it. For thousands of years, humans measured the cosmos using familiar ideas: distance, mass, brightness. We assumed that nature, no matter how large, would still feel understandable. Stars would be bigger than planets. Galaxies bigger than stars. Everything would fit into a hierarchy our minds could grasp. Stephenson 2-18 breaks that illusion, because its size is not just large, it is absurd. It stretches beyond intuition, beyond visualization, beyond emotional comprehension. We can say numbers. 2,000 times the sun's radius, billions of kilometers wide. But those are symbols, not understanding. There is no human-scale reference for something that could swallow solar systems whole. And when understanding fails, humility begins. This is why astronomers didn't react with celebration when its measurements stabilized. They reacted with caution, because extreme objects expose the edges of our knowledge, and edges are dangerous places. Every time science believed it understood limits, the universe produced an exception. Neutron stars defied density limits. Black holes defied space-time. Dark energy defied gravity. Now stellar giants defy size, not by breaking rules outright, but by showing how soft those rules really are. Stephenson 2-18 reveals something profound. Nature does not operate with neat boundaries. It operates with ranges, probabilities, conditions. Under the right environment, the impossible becomes permitted. Not common, not stable, but allowed. That alone should unsettle us, because humanity often assumes that what we see today represents the full range of what exists. History proves otherwise. We once believed the sun was the largest object, then galaxies, then clusters, then superclusters. Each time, we were wrong. Each time, reality expanded. Stephenson 2-18 reminds us that we are likely wrong again. There may be stars even larger, hidden behind dust or too distant to measure accurately. There may have been giants in the past that dwarf this one entirely, and there may be forms of matter yet undiscovered that make size itself irrelevant. This star is not special because it exists. It is special because it reveals how incomplete our picture remains. And that leads to a quiet existential realization. If the universe can build something this enormous, then human concerns are both insignificant and precious. Insignificant in scale, precious in rarity. Because size does not equal meaning. The universe produces giants effortlessly, but consciousness? That may be far rarer than stars. Stephenson 2-18 burns without awareness. It will live and die without memory, without curiosity, without wonder. We, fragile and temporary, are the ones who look up and ask questions, and that matters. Perhaps that is the final lesson hidden inside this impossible star. The universe is not gentle. It is not balanced. It is not designed for comfort. It creates extremes without apology. Yet within that chaos, tiny pockets of awareness emerge. Briefly, quietly, long enough to notice. One day, Stephenson 2-18 will vanish. Whether through collapse or explosion, it will end. Its atoms will scatter. Its light will fade. Its name will become a footnote in cosmic history. But the fact that we discovered it at all, from a small planet orbiting an average star, may be the more extraordinary event. A creature made of stardust measuring the things that created it, trying to understand forces that do not care whether they are understood. And maybe that is what makes the universe beautiful, not its size, but the fact that something so small can contemplate something so vast. Because when you look at a star that should not exist, you are not just looking at a cosmic anomaly, you are looking at a reminder that the universe is larger than our fears, stranger than our theories, and far more capable than we ever imagined. And somewhere, deep in the Milky Way, a giant still burns, silent, unaware, holding entire solar systems within its reach. While we watch from afar and wonder how anything, including us, exists at all.